Welcome, everyone. Thanks for joining us today. It's my pleasure to introduce our speaker, Dr. Tai Lee. Dr. Lee is an assistant professor of computer science at Indiana University's Luddy School of Informatics, Computing, and Engineering. Dr. Lee's research focus is on making AI and machine learning models more robust, safe, and transparent. He is a pioneer in studying text perturbations in the wild. His work has earned him multiple awards and has been featured in outlets like Science Daily and Defense One. Today, he'll be speaking on robust and trustworthy AI speech models. What you read isn't what you hear. If you have any questions during the talk, please use the Q&A feature at the bottom of your Zoom window and we'll address them at the end of the session. Dr. Lee, thanks for joining us. Please take it away.
Thank you so much, Mike, for the introductions. Good afternoon, everyone. So again, my name is Tyler. I'm assistant professor in computer science at Indiana University. It's a pleasure an honor to be here and present with you my work today. So today I'm going to talk about robust and trustworthy AI speech models. What you read isn't what you hear. So why speech? There are a lot of big push nowadays on AI. And if we look around, most of the work is focusing on text and images. So why speech? So to illustrate the motivations, I show on the screen the pictures, right? So this is a pictures of two people talking to each other in a restaurant's context. So if we need to build an AI model to understand these scenes or to understand these scenarios in real life, and if we use a vision model, maybe the vision model can recognize, hey, there are two persons speaking to each other in a restaurant, in a bench restaurant, and maybe the bench is yellow, for example, right? But beyond, if we only use vision features, we cannot interpret other properties of the screen. For example, what are they talking about? Whether they are husband, wife, whether they are boyfriend, girlfriend, whether they are colleges or friends, or whether they are strangers. As you might realize in our life, sometimes we walking in the eyes of a restaurants and we eavesdrops conversations in the nearby tables. Sometimes we can guess whether they are angry at each other based on the nature of the conversations and based on the speech of what they talking about. So as you can see, AI really need to incorporate speech to understand the nuance and complex scenarios in the real world. Moreover, we as humans, we communicate daily using speech. So as you can imagine, if we have an autonomous car, we cannot control the car by texting, right? So speech is a natural way that we human communicate. Also nowadays, there are a lot of on-device AI models that incorporate speech, such as the Meta glasses, or we have the real-life translation features on the Apple earpod. So speech AI is increasingly become more important in our life. The last example is speech can be also used as a means to authenticate our identities. So nowadays, if you call banking systems at Chase, they're going to ask you whether you want to use your voice to authenticate who you are. Right? So again, speech is needed for AI to fully understand, reason, and comprehend the world. And together with the technologies, as AI models become more sophisticated, there's an emergent artifacts is called deepfake speech. So deepfake speech are the recent capabilities of AI, especially generative AI model, to synthesize hyper-realistic speech. It is no longer what you hear, is what you believe. And on the right side is a snapshot of the news published in September 2025. And it says people cannot distinguish AI voice clones from actual humans anymore. And nowadays, when we go to social media, TikToks, YouTubes, we can see this is a real life scenarios. It's become very real in our life as we see more and more artifacts, machine generated, hyper realistic speech online. And together with these technologies, where it can help us in many facets of life, it also create a lot of unfortunate situations. On the screen is a news, recent news last year's where on online scammers, they use deepfake technologies to pretend or to impersonate Brad Pitt, and they're able to scam victims nearly £1 million. And similarly, we also saw this trend of malicious actors utilize the technology for impersonation. For example, scammers clone Italian defense minister voice with AI in ransom schemes. Or we also can see deepfakes and voice clones fuel over 100% search in AI impersonation scams. And deepfake voice scams are become more sophisticated. Nowadays, if we go to GitHub and Google, there's so many tools that are available to use and very accessible. And anybody can use them to clone and generate hyper-realistic voice. In October 2025, there is a report about voice phishing, or they often called phishing, right? So voice phishing surged over 400% in 2025, driven by AI clone, voice clone, and hybrid scams. And they estimate around over 40 billion projected loss. So to defend against these technologies or to defend against this deepfake voice, what the researchers in the communities, what we have been trying to do is to try to detect this model, right? So to detect this model, let's look at typical scenarios. Let's say we have a sentence or so-called utterance. So this utterance can be as simple as, for example, we want to say he got married. So this is what we read. And then we're going to fit what we read into the TTS, text-to-speech model. So the text-to-speech model is fueled or enabled by the reason generative AI speech, and they can generate hyper-realistic voice. And this become the acoustic signals or what we hear. And then what we hope to do is when we fit these acoustic signals into an AI model or a defect detection model, we will be able to accurately predict or distinguish whether this acoustic signal is a fake speech or generated by AI, or this speech is spoken by authentic human beings. So this becomes a classification problem. However, in these detection models, there are a lot of security risks we need to take into account. For example, in the literatures, what people have been working on is they want to test whether these AI models are robust in different acoustic environments. And these are often so-called acoustic perturbations. So they want to test whether the relationship between acoustic and AI models is robust enough. So to do this, what we often do is after we have the acoustic sounds or signals from the TTS model, they try to find some noise such that when they add the noise into the original acoustic signals, they're gonna able to fool the prediction model or the AI model to output a real speech instead of fake speech. So in this case, by inject the small noise into the acoustic signals, the malicious actors, or we can red teaming these AI models as not being robust. And we can imagine there's a lot of type of noise. For example, there can be a background noise. We can change the speed of the cells. We can stress the speed of cells. So you can see all this work. We have been focusing on making sure that the relationship between acoustic signals and the AI models is robust. However, beyond this, what can we do? Beyond this, what are the security threats that we can pay attention to and we can exploit? So, and that is the central message of these talks. So we ask a question, how about linguistic perturbations? So instead of injecting noise into the acoustic signals, what if we say things slightly different? So instead of saying he got married, can we change the text or the semantics of the utterance using some linguistic variants? So instead of saying he got married, can we say he just got married, or we say he just married, or we say he married? And you can see these different versions of the utterance or the text, they have similar meanings. So then maybe we can change the text and then we can input to the same TTS model and then we can get a slightly different acoustic signals. But when we input these acoustic signals, can we fool the AI models to output real audios instead of fakes? So in a sense, instead of exploiting the direct inference between acoustic and AI models, can we exploit the indirect inference between semantics or the utterance to acoustics and to AI models? So let's look at the examples. So we're gonna use the online bromance scam Brad Pitt that I introduced before as an examples. So let's do some preliminary tests. On the screen is the utterance A's, and the utterance A's has the highlighted word vital. And we also change, so what we do is we change the vital word to essentials. So we generate the utterance B. As you can see between the two utterance A and B, the only difference is one word. Instead of saying vital, we say essentials. And since the two utterances have very similar meanings, semantic meanings, maybe we hope that if we input the two utterances into the TTS model, we're gonna have the new voice that are somewhat similar. So I will play the voice, which is generated by a state-of-the-art TTS model using the utterance A. And then can you guess, if we input the voice into the AI detection models, whether the model can be accurate at predicting this is a fake voice or a machine generated voice?
Correctly. The doctors need payment now to proceed with this vital step. And you're the only person I can turn to in this moment of absolute crisis.
So that is the speech A. And let's hear the speech B. And when you listen to the speech B, you can see that essentially everything sounds very similar, except one word.
Exactly. The doctors need payment now to proceed with this essential step. And you're the only person I can turn to in this moment of absolute crisis.
Even though the messages have the same contents and there's no other artifacts in the audio, and you can see the audios, the AI models is able to clone the voice of Brad Pitt very well. However, if we input the first voice into the AI detection models, the predictions is 0.66% real. However, by only change one word and we input to the same TTS, we're able to fool the detection model to output the predictions this voice as 92.36% real. So essentially, by changing only one word out of nearly 30 word utterance, we're able to fool the AI detection model significantly. So this gives us conclusions, preliminary conclusions, that how to linguistically and semantically construct an utterance matters in defect detection models. And then this also introduced interesting security threats. So imagine we have a conversations between the victims and the malicious persons, and the malicious persons can only need to change one word out of what he or she wants to say, and he or she will be able to fool or invade the audio defect detection model significantly. You can see on the first transcript, the malicious person say, and I need to be direct. But by changing need to should, you can see the prediction probabilities of this audio as real humans increase from 0.1% to as high as 81%. And in the second transcript, similarly, by changing two words, critical and funds to central and fund without S, the malicious actors able to fool the detection model from 0.3 real probabilities to nearly 80% real probabilities. So to summarize, in the acoustic attacks, what we want to exploit, if we want to exploit the direct relationship or direct inference between acoustic and AI models. And the way we exploit is we add the noise directly onto the acoustic signals. However, in the case of linguistic attacks, we want to explore the indirect relationship between utterance, semantics, acoustics, and AI models. So for example, on the right side, given a transcript, grammar, oh my God, grammar, you have to help me, I'm in trouble. What we can do is we can add some semantic level of text. For example, we can change the in trouble to dangerous. So by changing just a few words, we can still maintain the semantics of the message. However, the final speech is able to fool the detection model significantly. So to push this linguistic attack to the limit, we design an algorithm called TAPAS, transcript to audio perturbation anti-spoofing. So our objective functions is straightforward. So we want, given a speech AI detection models, we're gonna ping the AI detection models multiple times. And every time we ping the detection models, we will try to find what word in the transcript we can perturb in such a way that we decrease or increase the prediction probability significantly, such that it change to a different class. And due to the time limit, if you're interested in the algorithms, I would love to discuss this offline. But our algorithm is able to attack the state-of-the-art AI detection models in a black box manner. So we don't need access to the model parameters or the architectures. In real life, this black box text is very powerful. As you can imagine, if the attackers have some query access to the detection models, they can exercise this attack and they can optimize the transcript, or they can optimize how they say a message in such a way that when the message is transformed into the speech will be considered as a real human speech by the detection model. And these are some of the results that we have. So first, we test with open source detection models. This is a tables, and this detection model is called ASIS. And let's first look at all the metrics. The first metric is OC, the original accuracies. And on the left side is we test with different text-to-speech. Kokoro is a very popular lightweight text-to-speech model, and similarly CoQ. And here we try to impersonate different voice profile. For example, we try to impersonate a British male, British female, American voice. We try to impersonate famous people as well. We also test with F5, which is a recent TTS model. So as you can see, the detection models, without any attack, the detection model perform very well, and they're able to detect the fake examples nearly or even over 90% accuracies. However, under text, we also measure ASR. ASR is our attack success rate. So if we're able to fool the detection models to predict a fake voice as a real human spoken voice, it is considered as a successful attack. So as you can see, we're able to achieve very high attack success rate, sometimes up to 80%. And interestingly, we observe a trend that the female voice profile is easier to attack than the male's voice profile. And you can see in the last rows, even with the state-of-the-art TTS, we're able to achieve attack success rate to 62%. And the same trend also in the COS metrics. So COS metrics measure the semantic similarities in the utterance before and after perturbations. And to measure the COS, we measure the cosine similarities between the semantics vectors of the utterance before and after perturbations. And you can see the new utterance or the perturbed utterance still reserve majority of the semantic meanings of the original sentence. And we also observe the same trend in other state-of-the-art detection model, for example, CLAP and RONET2. All of them are very popular in deepfake speech detection model. And beyond testing open source model, we also test with commercial detection models. In here, we test with an API we call API A, and we test with different commercial TTS as well, including OpenAI in the last row. And you can see the original accuracy. Commercial detection model do a fantastic job in detecting these TTS model, including OpenAI whisper text-to-speech model. However, under our text, by slightly change the utterance on the transcript underneath the speech, we're able to achieve up to 66% attack success rate, even when we use the OpenAI whisper model to generate the speech, and while reserving the semantics nearly 90%. As you can see, our text linguistic perturbation attacks is generalizable and successfully do black box attacks for both open source and commercial detection models. So if we can imagine, if we have a defense systems where we use commercial detection models, it doesn't guarantee that the model going to be robust against slightly perturbation or slight changes under how the utterance is constructed linguistically and semantically. Beyond testing on these state-of-the-art audio deepfake models, and most of them are classical deep learning models, we also test our algorithm against reasoning audio models, which are the reasons development in speech AI. And when we test with acoustic perturbations, we achieve 40% attack success rate. And when we test linguistic perturbations, we also achieve as high as 20% success rate, even though these reasoning audio model are pre-trained on a large amounts of audios and speech. So say the audio reason models are also vulnerable against this linguistic attack. Now let's look at the case studies. How can we apply these observations about linguistic sensitivities on the problem of speaker identifications or speaker representation learnings? And this problem is this task is very applicable in our life, because nowadays there's a lot of systems they authenticate our identity using voice, especially a lot of banking system for examples. So our results show that if we do a voice cloning attacks, for example, let's say I want to steal the identities, or I want to authenticate identities of a target victim A, I can get some short audio of the person A, and I can use a simple TTS attack, or I can use a state-of-the-art TTS to voice cloning this person. And we show that over 90% of deepfake examples can bypass the authentication systems. And now if we combine this voice cloning attack with our algorithm, which is TAPAS, so of the remaining examples, our linguistic attacks can reinforce and results in 48.3 success attacks rate. So in an essence, we can bypass voice-based authentication models with over 95% success rate, with just a brief real voice recordings. And on the screen on the top right is the representation visualizations of how the real speech, of how the speech vectors changes their position over time. And let's zoom in one particular data point here. So the circle represents the real voice recording of the real persons. And after we use deepfake speech generator to clone these people's voice, the vectors of this, the vector representations of this person move further away according to the blue arrow. However, after we use the TAPAS attacks, or we change the linguistics framing of the utterance, we are able to pull it back towards the original directions toward the real voice. And by doing this, we can fool the speaker representation learning algorithms or the speaker identification system. Beyond showing this attack work, we also try to understand why this work. So on the right side is a table listing on the features that we think is influencing the deepfake detections more model decisions. For example, let's look at the features audio encoder similarities. So we hypothesize that. If the audio encoder is a modules that encode the sounds to the vector representations. So if the audio encoder of the detection model is similar to the audio encoder of the speech synthesizers, then the model gonna become more robust because it's able to capture the nuances in the speech synthesizers. And we confirm this hypothesis on the graph on the left side. And you can see as the audio encoder similarity increase over times, the effects on predictions decrease over times, meaning the similarities between the audio encoder, between the detection model and the synthesizers, the more robust the detection model becomes. The second hypothesis we make is we ask a question why when we change the linguistics structures, only a few words is able to change the decision models. We hypothesize that maybe when we change the words, we change the PPL or the perplexities or how fluent the text is. So, but from our findings, this is not really the case. So even when we train the detection models from fake and real speech with exactly the same utterance or transcripts, meaning when we make sure the training data has no bias in terms of linguistics, the differences between fake and real, we still achieve a very high success success rate, as you see on the screen, up to 36 and 47%. So this shows that there's something else that influence the indirect influence the relationship between utterance to acoustics and to AI detection models. And from the table on the right side, when we use all these features to predict the linguistic sensitivities, we can achieve an F1 score of 77%. And you can see there's still some room for improvement, meaning there might be other dimensions or other features that we have not accounted for in capturing the relationship between utterance and AI detection model. So this is still, there's a lot of room for improvement. And one thing we have not understand is maybe this is an out of distribution problems, which is a very popular reasons or explanations for adversarial robustness for AI models. However, in our problem, it is not out of distribution, one step out of distributions, but it's a two-step out of these distributions. So maybe we have our distributions from the utterance that affects the generations of the speech, and maybe we also have another output distribution problem from the acoustic speech to the AI detection models. But we don't know whether is it one happens, is it two happens, or both of them happen at the same times. So this is one of the limitations that we want to improve upon. We want to model the complex indirect effects of semantics, acoustics, and AI detection model as a full end-to-end analysis. So what's next? So this work implies a lot of interesting future directions. First of all, of course, how can we then build a robust and secure AI systems? Because in real life, especially when we interact with robots in the futures, and even nowadays, seems like how we speak or how we frame the message is also important because it influences the sensitivities of the AI model predictions and the decisions. And linguistic sensitivities goes also beyond defect speech detections. How about what effects of these phenomena on other tasks, for example, robotics, embodied AI, emotion detection, for example. And then how can we train humans to what to say and how to say so that AI can examples in authentication systems. So by saying this, I conclude the presentations, and I would love to take on questions. Thank you so much, everyone, for listening.
Thank you so much, Dr. Lee. Yeah, so if anybody has any questions, please put them in the Q&A. So what are there any ways you could think of that like your system could be exploited or attacked?
Yes, that's a very good question. So, yeah, our work findings is essentially even state-of-the-art open source or commercial defect detection systems. They are not really robust in real life. And as you can see that there are constant cat and mouse game between the synthesizers and the detection models. And as we can see, the quality of the generated speech is increasing, becomes really good over time. So at the same time, we need to make sure that the other side, the detection models, is also robust, not in terms of how the acoustically these systems generated speech, but also how it correlate with the underlying transcript and utterance. And so, yes, this is still a very open-ended research question.
I see.
Yeah.
So like could like the content of the message somehow like influence or like mislead the model? Or like I know it's acoustically, but like would would the content somehow sway the model possibly to maybe misidentify?
Yeah. So, yeah, so I think that's an interesting question because when we work on speech, we often only think about the acoustic signals, like like the pitch, the tone, whether we have some pause in our speech, right? But it seems like the contents of the speech it affects how the AI generator they synthesize the speech, and we have not really understand this very well. Because most of the time we only focus on, hey, speech is an acoustic issue, right? But it turned out, no, speech is actually a fusion between text and acoustics. And that's make is a very interesting broad problem. And maybe if we think about parallel scenarios where we want to detect deepfake audio, for example, right? So in deepfake audio, if we can imagine on the audio, there might be some text appear in the audio. And you can see it's a fusion modalities, right? Speech is not like we have multimodal modality where we have input a text and we have input a speech. No, it is fusion together. And when it fusion together, it is a very interesting research problem.
I can see it. Well, I recently heard about a way to basically bypass a model's like guardrails. Maybe putting in like something into a prompt, that makes it
Mhm.
more positive than a negative kind of thing.
Mhm.
I mean, do you see like something similar to that with what you've been doing?
Yeah, absolutely. So recently, a lot of industries research lab, they're trying to develop a conversational chatbot. So basically, we're not texting to the bot anymore, but we are speaking or talking to the bot, right? And you can imagine, we can transfer all the research from text space into the speech space. For example, instead of jailbreaking, or like fooling or forcing the model to say a certain things, for example, how can I make a bomb in a text?
Right.
Then we can transfer further to speech space, right? So I can imagine this model gonna have some guardrails.
Yes.
However, if we apply this work into that situations, how we say it, how we say things is also important, right? Because what we realize from this work is, hey, not only the pitch, the tones, but also how you say things is important, right? And so yes, I do feel like there's some parallelism between LM safeguarding and conversational chatbots.
Okay. Yeah, we have a question here from Christopher. So are different languages easier or harder to detect AI versus authentic audio? And I know you've mentioned, different accents, but in
Yeah.
English, but what about different languages?
Yeah, this is an excellent questions. We have not tested on models, non-English model in other languages, and I believe the multilingual deepfake speech detection is still an open-ended research scenarios. But my guess is some language gonna be easier or harder. It really depends on how the speech synthesizer work, right? For examples, one issues that we have not talked about um, is how the word they affects the synthesize of that word in the acoustic domains, and sometimes we speak a word differently as well, depends on different contexts and emotions. And another interesting scenarios that we're working on is in the code switching context. So let's take misinformation detects as examples. Um, Statistics show that most of the fake speech and videos, they're not in English. They actually in other languages like Spanish, for example, right? And if you can imagine, if somebody is using Spanish and English at the same times in the same sentence, how that going to affect defect detection models. And you can see the multilingual aspects really expanding this work, and make it some very interesting research question to solve. So yes, I don't know whether one language is, maybe Spanish is harder to detect or harder to attack, but I can imagine there are going to be some differences among languages.
I see. Great. Okay, if anybody else have any questions, please put them in the Q&A. Okay, it looks like we have another one from an anonymous. Are there any research opportunities with AI speech models
Yes, as I mentioned, this is a very still open research questions. And as we see the field moving, for example, recently we can see the developments of live translation on after EPUB. And recently we can see a lot of development in meta classes and things like that, right? So definitely AI speech model, especially real-time AI speech model, it's going to be interesting research directions. And please feel free to contact me to my email, and then we can discuss potential collaborations. Yeah.
Okay, I'm not seeing any more questions, but if we do, I'll be sure to send them along to you, Dr. Lee. But thank you very much. Really appreciate it.
Thank you
Thanks
so
for
much
joining
again
us.
for having me here today. And please feel free to contact me if you have any further questions regarding in any chat regarding trustworthiness of AI speech model. Yeah.
All right, great. Thanks a lot. Take
Thank
care.